I'm Fengtian from Tsinghua University, China. It's a great pleasure to be here and honor to present our research about a sensitive micromachined accelerometer based on a electrostatically suspended proof of mass. First, the background of our research. Super-sensitive electrostatic accelerometers are widely used in microgravity space missions, such as satellite gravity gradiometer and other fundamental physics experiments in space. The traditional electrostatically suspended accelerometer can offer extremely high resolution below pico G by setting ultra-low input range on the order of milli-G to micro-G. However, these space accelerometers are inherent in costly machining and large size, which limits their potential application in growing small satellites. Here, I will present a silicon-based electrostatically suspended accelerometer with an extremely low input range on the order of milli-G. Now I'll talk about our work. First, Accelerometer Geometry. This MEMS device, schematically illustrated in this figure, is a silicon glass sandwich structure with a square proof of mass suspendedly electrostatically in 6 degrees of freedom by surrounded electrode. In our sensor design, the proof of mass and the lateral electrode are arranged at a home tool structure in order to maximize the sensitivity of the position sensing. Moreover, separated lateral sensing and electrode are designed in order to achieve low input range and thus high sensitivity. This figure shows a schematic arrangement of sensing and forcing electrode for control of the motion of a free proof of mass in 6 degrees of freedom. This device present here is a silicon glass sandwich structure. Was made 3 wafers. One is the silicon wafer and top bottom glass slab. Next, fabrication of this MEMS device. This figure is a complete fabrication-Process of the device. The device present here is a silicon glass bonding device using bond micromachining technique. A fabricated chip and its package are shown in this picture. The device parameters of the prototype device are listed in this table. The side length of the proof mass is 3.5 millimeters. Its thickness is 88 micrometers. Now let's move on to electrostatic suspension of the proof mass. The motion of the proof mass is fully servo-controlled by capacitive position sensing and electrostatic force feedback. This figure is a schematic drawing of the capacitive position sensing circuit. The output is proportional to the differential capacitance and thus to the off-centering of the proof mass. In our sensor, there are totally 7 sensing channels to obtain the motion of the pull mass in 6D or SFS, as shown in this picture. One high-speed gas-based suspension control operated at a 10 kHz sampling frequency are used to achieve stable suspension of the mass. Since 3 linear acceleration and 3 angular acceleration can be measured from applied suspension force using only one device, this accelerometer can be functioned as a 6-axis inertial sensor. Now, electrode configuration. In following test, the electrode in Z direction and Y direction are configured as multiplied sensing and forcing. They are connected together. However, on the X direction, this direction, we use separate sensing and forcing electrode in order to achieve low input range. Additionally, the input range in this direction is will set a larger value over 3G in order to counteract the force of gravity. In the sensitive X direction, the input range was set as low as possible in order to obtain high sensitivity. The experimental setup is mainly composed of 2 stacked PCB, one for position sensing and one for suspension control. One device mounted on the top PCB and associated electronic instruments. This figure shows the measured position response of 4 channels along the Z direction. The leveled up time of the pull mass is limited from the bottom plate to the center of the cavity is about 2 seconds in atmospheric environment. The experimental results of closed loop frequency response are shown in this figure. To illustrate the dynamic performance and stability of the suspension loop, it can be clearly seen that these responses are quite different between the Z direction and X and Y suspension loop due to difference of viscous damping in effect. Simulation results show our film damping coefficient in Z direction is more than 2 orders of magnitude larger than that in lateral X and Y axes. Additionally, by setting the bell from 5 to 1 voltage, the bandwidth was reduced accordingly from the red line to blue line. A plot of measured suspension stiffness is shown in this figure. It can be observed that the lateral suspension loop behaves extremely low suspension stiffness compared to that of Z direction. One of design considerations in this step suspension loop is that the stiffness characteristics must match the full range of the accelerometer. The Z direction have a large range, so it has a higher stiffness. Finally, the experimental results of accelerometer. This table presents our overall performance of the prototype 3-axis accelerometer. The belt was initially set on each axis was 5 voltage. Later, the sensitive X direction was reduced to 1 voltage in order to lower its range and increase the sensitivity. The initial test of the sensitive X direction show a full range of 61.6 millig and a sensitivity of 162.4 voltage per G was achieved by setting the bias at 5 voltage. By setting an extremely low bias at 1 voltage, a full range of 2.9 millig and a sensitivity of 688.8 G per voltage per G was achieved. The measured noise using a dynamic analyzer was are shown in this figure. The equivalent noise in these 3 cases are all on the order of 1 times 10 to minus 5 G per square root hertz. Although these 3 cases, the input range are quite different. Perhaps the measured noise are limited by land seismic acceleration or less. To end my presentation, I would like to point out the following 2 aspects. The ground test shows that this accelerometer can offer extremely low full range and thus high sensitivity. Second, on ground test of the sensitive accelerometer are limited by the presence of 1G gravity and land seismic noise. Thank you for your attention.